The third law of Kepler consists in a universal proportionality between two magnitudes that characterize the orbital motion of a planet: the semi-major axis of the ellipse traveled by the planet, and the period of time that it takes to complete it. Precisely, the proportionality is the one between the cube of the semi-axis and the square of the period. That is, a cubed divided by t squared is equal to a constant. How did Kepler get to his discovery? First of all, the German mathematician and astronomer had access to the very accurate observational data gathered by Tycho Brahe during the years. Later on, he nourished a fundamental attitude for a scientist. He believed that natural phenomena follow a well-defined scheme that the human ingenuity could unveil. Finally, he was convinced that these schemes were expressible in terms of relations between numbers. Therefore, Kepler was fascinated by numbers and their hidden explanatory possibilities. Let's try to understand which was his modus operandi with a few simple examples. Let's begin by observing a sequence of numbers: 2, 5, 8, 11, 14. Which number will come after? Exactly, 17. How did we do it? We formulated a hypothesis. One moves from a number to the next one by adding 3 units. Then we test it and we found out that it works. Another example. Which number completes the sequence? 1, 1, 2, 3, 5, 8, 13. That's right, it's 21. We're talking indeed about the renowned Fibonacci sequence. Every number is the sum of the 2 preceding ones. Problems like this challenge our ability to define regularities, to formulate hypotheses, and to test them. Now, let us see a simplified version of the problem that Kepler cared most. Let's suppose we have the following data for 2 planets. Planet A has semi-axis A that equals 1 and period t equals 3. Planet B has semi-axis A that equals 2 and period t that equals 6. Therefore, we can imagine that the rule could be t equals 3 times A. But then we discovered a third planet, C, for which we observe that A equals 4 and t equals 18. Our former conjecture, namely that the period is the triple of the major semi-axis, is proven wrong and so must propose a new one. After some attempts, we realized that a new rule, t equals a squared plus 2, works for all the 3 planets. Obviously, the validity of the conjecture remains at risk. We have to look for another planet and test it, and, if it fails, change it accordingly. This, very briefly, is the kind of work done by Kepler. However, often in physics, finding an algebraic description of the phenomena is not enough. One instead looks for a dynamical description that takes into account the causes of an event and how they affect it. Concerning the planets, this will happen 50 years later with Newton's work. From his principle of dynamics, indeed, it's possible to deduce also the third Kepler's law. Analogously, physicists began to study the atoms by elaborating an algebraic scheme for the light frequencies emitted by them. Only some decades later, first Niels Bohr and then Erwin Schrödinger developed more general theories by which that algebraic scheme was proven correct.